This function is very curved. If it's like this, then, so that's high curvature, then you want to take a small step. And if it's low curvature, then you want to take a big step. And you would you'd put the second derivative into this formula also. But computationally, second derivative methods are very tricky. The second derivative can be difficult to compute. It can be numerically unstable, and it's got another disadvantage that I'll mention in a few minutes. But almost whatever method we want to use to maximize conditional likelihood and train logistic regression, we need to compute this derivative, d by d beta of the log conditional likelihood. So now that's what I'm going to evaluate. And it turns out to have a very elegant, it comes out to be a very elegant expression, and it comes out to be something very similar for the general case of log linear models. Okay, so I have my parameters alpha and beta 1 to beta d. So now, first I'm going to simplify. I'm going to define alpha equals beta 0 and let x0 equals 1 for every x bar. So remember, the expression that I had was alpha plus sum from I equals 1 to d of, or j equals 1 to d, beta j xj. And so now with this simplification, this is going to be sum from j equals 0 to d of beta j xj. So now I don't have to treat alpha separately from the betas. I can just treat all the betas the same. Okay, so now I want to evaluate, so d by d beta j of the log conditional likelihood for all j. And the log conditional likelihood is the sum from I equals 1 to n of the probability of yi given xi and given the beta parameters. And so everybody clear why this is the log conditional likelihood? And then I'm going to separate this out into two parts. So the I, such that yi equals 1, plus the I such that yi equals 0. So every training example has a particular value for yi. And that particular value is going to be either 0 or 1. So I can just group the training examples according to their value for yi. And so this will be probability of 1 given xi, and then probability of 0 given xi beta. Okay. And the reason I'm doing this separation is that, the formula for probability of 1 is different from the formula for probability of 0. And so I'm going to treat these separately. Okay. So now d by d beta j of log conditional likelihood. So remember, the derivative of a sum is the sum of the derivatives. So this is, so sum from I such that yi equals 1, d by d beta j of, okay. So I forgot the logs in here. The likelihood would be the product of the probabilities. And the log likelihood is the sum of the log probabilities. So I need to put in these logs. Log p of 1 plus sum of all I such that yi equals 0, d by d beta j of log probability of 0, and then same as before. So now again, changing my notation a little bit. Sum from I equals 1. So such that I'm not changing the summations. I such that yi equals 1, d by d beta j log p. So I'm just going to call this p. And then this is 1 minus p. Because the probability that y equals 0 is 1 minus the probability that y equals 1. D by d beta j of log of 1 minus p. Okay. So everybody see how I got to here? So now I'm going to really start work. I'm going to evaluate d by d beta j of log p. And this is 1 over p d by d beta j of p. There's the derivative of the log function. This is the natural log function. So the derivative of the log is the 1 over function. And d by d beta j of log of 1 minus p is 1 over 1 minus p, and then minus 1 d by d beta j of p. So in both cases, now what I need to evaluate is this. Okay. So drop the cap. Hope it doesn't dry out. Here it is. I found it. Okay. So let me introduce some notation. So E is the exponential of my linear function minus sum from j equals 0 to d of beta j xj. And then P is 1 over 1 plus E. So this is my logistic regression function. And 1 minus p is, so over 1 plus e, and then 1 plus e minus 1 is e over 1 plus e. And okay, so I use that notation. Then d by d beta j of p, see that's the thing I need to work out here. It's, and this is the definition of p. So it's minus 1 times 1 plus e to the power minus 2 times d by d beta j of e. And so minus 1, 1 plus e to the minus 2. And then this is, e is an exponential function. So the derivative of an exponential is the exponential. So I get e, and then d by d beta j. And now I'm taking the derivative inside the exponential, which is a linear function. So I just really pick out the term here that involves beta j. And that is minus xj. So I've worked out the derivative. And then now comes the elegant rewriting part. So I can cancel these minuses, and then what I get is 1 over 1 plus e, and then e over 1 plus e, because I had a 1 plus e to the power minus 2 here, times xj, which is p times 1 minus p times xj. So I've written the derivative of p in terms of p. So this may look a little bit circular. I mean, I've written the derivative of p in terms of p. But it's just saying, you know, the numerical value of the derivative is this function of the numerical value of the function itself. And if I was coding this up, you know, I write a line of code to evaluate e, then I write a line of code to evaluate p, a line of code for 1 minus p, and then the next line of code, I can evaluate the partial derivative. And you know, this, so what it says is that really for every beta j, the partial derivative is proportional to xj. Because all this will work for any j. And so I can fill in here now. So this red box is this. So I put it back in here, and the p's cancel. I get 1 minus p xj. And I fill in here, and the 1 minus p's cancel, and I get minus p xj. Okay. And now, what I have here is these are the derivatives for a single training example. So a single training example is a single x value, a single y value, and correspondingly a single p value. The derivative for the whole training set is the sum of these derivatives. So d by d beta j of the log conditional likelihood is the sum from the sum for the positive training examples, that's the i's with yi equals 1, of 1 minus pi xij. So xij is the jth feature value for example number I, and these examples number I have positive labels. So what I need to use is the derivative of log probability. But then I have sum from I such that yi equals 0 of minus pi xij. And now I'm going to use just a notational trick. Sum over all I of yi minus pi times xij. So this is really a trick. For these i's, 1 is equal to yi. So I can write yi instead of 1. And then for these i's, yi equals 0. So instead of writing 0 minus pi, I can just write yi minus pi. So put them together, I get this. And okay, I'm going to erase everything else because this is now I just want to focus on analyzing this result for a minute. So you see the partial derivative of the log conditional likelihood turned out to be something very simple and elegant. And remember the Bernoulli example. So what's the easiest way of actually finding a maximum? Easier than doing hill climbing. Yeah?
Just count the outcomes of the 0.
Okay. That's what we work. That's what we worked out. But sort of the principle we used was set the derivative equal to 0. Yeah. So let's say, okay, set d by d beta j of log conditional likelihood equals 0. Maybe we'll be able to solve this equals 0, maybe we won't. What do we get? We get, so this is sum over I of yi minus pi xij. So we get sum over I yi xij equals sum over I pi xij. So remember, this is over the training data, and the yi's are the training labels, and then the pi's are the predicted probabilities for the training examples, and this equality is going to be true for the trained model. So yi equals the training labels, pi equals predicted probabilities by the fully trained model. So can somebody explain? So intuitively, what's it saying that this sum equals this sum?
So you want to train a model if the label is 1, the probability should be equals to 1. The label is 0, the probability should be equals to 0.
Yeah, this is the sum of all training examples. This is the sum of all training examples. So this is not really saying anything about any individual training examples. It's only saying something about the training set. So what is it saying about the training set? So here's my interpretation in English of what it's saying. So take any feature, xj, and take its total value in the training set for the positive examples. So here we're taking any feature xj, and then we're summing over the training set, but we're multiplying by yi. So we're really only summing. So sums over I such that yi equals 1 of xij. So maybe this is the most informative way of writing it. So the sum over the whole training set, the sum over all the positive training examples of xij, is the sum over all the training examples of xij times pi. Yes. So this is the expected value of xj, where the expectation is according to p. And this is the okay, yeah. So so the p's, the predicted probabilities you get for the training set are they're typically they're non-zero for every training example, but they have to spread themselves out so that for each feature, the average value of that feature for the positive examples is the same as the weighted average value of that feature for all the examples using the predicted probabilities as the weights. I mean, here's a special case. So sum over I such that yi equals 1 of xi0 is sum over I pi times xi0. And what did we say xi0 equals? xi0 is a constant 1 for every example. So this is the count of positive training examples, and this is the sum of predicted probabilities for every training example. And so what it says is the sum of predicted probabilities for all training examples has to end up being equal to the number of the number of true training examples. So this is this tells us in a way that the predicted probabilities have to be well calibrated, because when you add up over the whole training set, the number of positives equals the sum of the predicted probabilities. But this result is true for every feature. And there's something interesting to note is, supposing you have n training examples and d features, or d plus 1 features. How many equations of this type do we have? We have d plus 1 of these equations, one equation for each feature. And have I said anything about the relationship between n and d? Is n bigger than d or vice versa, or we don't know? The answer is that I haven't said anything, we don't know. And Normally when you think you have, if you think you have k simultaneous equations, if you have k simultaneous equations and they involve m unknowns, then if m is less than k, you have multiple solutions. If m is bigger than k, then you have no solutions. And here I have d plus 1 equations, and they involve n unknowns, which is the probability pi. And so generally, if n is bigger than d plus 1, then these equations may not have a unique solution. And if n is less than d plus 1, then you might think that it's possible that these equations don't actually have a solution. But it turns out they always do have a solution. But you can't actually do the training by solving these equations. I don't know any proposed training algorithm that actually solves these equations. What you can do is use these equations to check the result of any other training algorithm. Because whatever training algorithm you use, it should give you these training probabilities, and then these equations should be true, and that's what you can use that as a check on your training algorithm. And it's quite a strong consequence that the average value of any feature should be the same empirically with the training examples weighted 0, 1 and using the predictions. Okay. Now that I've so I worked out the derivative, and this is the derivative over the whole training set. So I could plug this derivative into a numerical optimization algorithm that uses derivatives and train logistic regression that way. But there's an alternative which is called stochastic gradient ascent. Stochastic gradient ascent. Okay. So the idea is compute the derivatives for one example at a time. Then update the model after each example. So let's try. Okay. So let X and Y be a single training example. And compute d by d beta j of probability of y given x and beta. And then do an update equals okay, I don't have a notation for this in my notes, so I'll just call it GJ. Then do an update, beta j gets beta j plus lambda times GJ. And so we do this in a loop structure, so for all x, and then inside for all beta j. Whereas, so this is stochastic gradient ascent. And then regular gradient ascent would be like this. For all x, so, for all. So in regular gradient ascent, you'd do the update one parameter at a time. And then for each parameter, you'd calculate the derivative with respect to that parameter. And the derivative with respect to the parameter involves iterating over the whole training set. With stochastic gradient ascent, you do it one training example at a time. So for all x is the outer loop, and then the inner loop is for all beta j. So for each example, you update all the parameters. And an algorithm of this form is going to be suitable for streaming data, because you could get the x's one at a time, and then after each x, you update your model, and then you go and take your next model, you take your next example, and you update your model again. And an algorithm like this is only going to be useful if you can hold all your training data in memory. So there's a fundamental difference. Okay. So again, I'm going to use the log probability. And what I have is that I calculated this before. D by d beta j of log probability of y given x and beta is it's y minus p times xj. So the update is, so for all x, and then for j equals 0 to d, do an update beta j gets beta j plus lambda times y minus p times xj. So I guess here what we would do is compute p. So we get a training example x. We compute its probability p according to the current model. And then for parameter beta 0 to parameter beta d, we update that parameter. And we update the parameter by adding something to it, which is the step size. And then the partial derivative. Then after we've done this loop over the beta j's, we've finished learning from this example x, and we can move on and learn from the next example x.
Why is it stochastic there?
Okay, so the reason it's called, the excellent question. So the algorithm itself, or most implementations of the algorithm itself are not stochastic in any way. It's called stochastic gradient descent because if you, so think of this example x as being a random sample from the whole training set. And then this is the derivative with respect to the single example. So if the single example is a random sample, then this is sort of a randomized approximation to the true derivative. The average right-hand side here will equal the true derivative. But each individual right-hand side here is just a random approximation of the true derivative. And that's why it's called it's called stochastic gradient ascent. So it's ascent according to a stochastic approximation to the gradient instead of ascent according to the exact gradient.
So it seems that you could be led astray quite easily if your stream of examples was not sufficiently random.
Yes and no. So the applications of this that I have personal experience with all involve training sets that are in fact finite and fixed. And then the thing that you always want to do heuristically is sort those into a random order so that so that each prefix of the stream is representative of the whole stream. If and you want to be able to throw away each x after you've trained from it, then I think to get some probabilistic guarantees, you do need to have some assumptions about how your training data are coming in random order. But that's I think just a special case of the assumption. So normally we make the assumption that training data are representative of test data. And I was talking about how here you don't need to necessarily assume that the x's are representative of the training x's are representative, but you do need to assume that the x to y mapping stays fixed. And if your training data are a stream and the first part of the stream is not representative of the later part of the stream, then I'm not sure that any learning method can be successful, because every learning method is just going to use the first part of the stream somehow and come up with some model that seems to work on the first part of the stream, but then it's not going to work on the second part of the stream. And there are stochastic gradient ascent is closely related to other algorithms, including the perceptron algorithm, which are non-probabilistic and which are directly designed for stream data and which give you guarantees that are called regret guarantees, which is that your so with an online algorithm, so here the situation is that we're using stochastic gradient as a training method. And we still think we're going to train, and then at some point we're going to stop training, and we're going to have a classifier, and then we're going to use it. But the online situation is that you get examples one at a time, you have to make a prediction for this specific example, and then you can learn from this specific example, and then you move on to the next example. And then a regret guarantee is a bound that the algorithm you're using is not going to do more than a certain factor worse than the best possible algorithm. And stochastic gradient algorithms can have regret guarantees, but I'm certainly not going to get into that now. But the algorithm, in practice, the algorithm is very useful for a lot of reasons, and one reason being that it's so easy to implement. And yeah, okay. So okay. So we're going to take a break in a few minutes, I think. I'll just so this is the algorithm. Now I'll just mention some heuristics that make it more useful in practice. So maybe the most important is scale each feature xj to have mean 0, or I'll just say same mean and variance. So it's not going to work well if you have some features, maybe like age, which range between 0 and 100, and then other features that range between 0 and 1. Because the dynamic range of the first feature will be 100 times the dynamic range of the second feature. And this lambda is the step size, and typically you only have one lambda. You don't have a different lambda for each j. And so for a single lambda to be a good choice, all the xj's have to be in the same ballpark. And since the feature x0 is constant equal to 1, it's reasonable to scale every other feature to have maybe mean 0 and variance 1, or mean 1 and variance 1. You have a lot of binary features which have the value either 0 or 1. So it's reasonable to not scale those and then scale every other feature to have mean 0 and variance 1, for example. And so I already mentioned, sort the training examples in random order. So some terminology. So one update for each training example. Is called an epoch. So an epoch means going through the training data once. And then the choose lambda based on trial and error. So what that means is that there isn't any good rule of thumb for how to choose lambda. It's going to depend on your particular learning problem. But lambda is just a single real number, so it's not too difficult to try some different values and find one that seems to work well. So, e.g., lambda equals, you might try lambda equals 10 to the minus a for a equals 6 to 0. And one of those lambdas is likely to work pretty well. And one thing you can do also is, if you have a very large training set, just take a small subset of your training set and then search carefully for which lambda works well on that small training set, and then use that lambda on the big training set. So searching heuristically for a good value of lambda doesn't have to be very expensive computationally. Okay. So fourth heuristic. So actually, you have a choice. So fix one good lambda, or start with larger lambda and then decrease regularly. And decreasing regularly, it could be per epoch, or it could be per example. So if you're doing it per epoch, maybe you're going to multiply lambda by 1/2 after each epoch. If you were doing it per example, maybe you'll multiply lambda by 0.999999 after each example. And the intuitive idea is that you want to start out with taking big steps because you're far away from the optimum and you're not so worried about overshooting. And then as you get closer to the optimum, you want to take smaller and smaller steps because you don't want to overshoot the optimum. You want to get closer and closer to the optimum. If you just try to fix one good lambda, then you only have one parameter to search by trial and error for its value. If you start with a larger lambda and decrease it, then now you have two parameters that you need to search for good settings for. So there's a trade-off there. Okay, I think that's what I wanted to say about stochastic gradient for logistic regression. And so when we come back, I'll talk about log linear models.
What are good packages?
Sorry?
What do you consider as good packages for logistics?
Okay, for logistic regression, I don't know. There's many good implementations available, and the most implementations of logistic regression don't use stochastic gradient because there are alternative ways. You can solve logistic regression problems using matrix calculations, where you essentially what you're doing, it's called iterative IRLS, iteratively reweighted least squares. So least squares refers to standard linear regression, and so you can solve a logistic regression problem by solving a series of linear regression problems. And then the linear regression problems you can solve using matrix operations. And so for small data sets, for small and medium data sets, this may well be the best method for solving your logistic regression problem. I'm talking about stochastic gradient because it's so easy and elegant, and it has so many extensions and variations, whereas this is much more specialized. But in MATLAB or SAS or R or any of your other favorite machine learning data mining programming environments, almost certainly there's a good implementation of logistic regression already. But it's very educational to implement it for yourself from scratch. And when you're doing that, then stochastic gradient is the easiest and I think gives the most insight.